Thank you very much, and thank you all for coming to my talk. My name is Whitmire. I'm a fourth-year PhD student at the University of Washington. My research focuses on sensing and interaction techniques to enable new kinds of mixed reality experiences. I'm really excited to be here today to talk about a project from Microsoft Research called the Haptic Revolver, a reconfigurable VR controller that lets you experience various haptic experiences. I want to thank all my co-authors from Microsoft Research. So if you consider today's VR controllers as input devices, they're really great for input. They have 6-DoF positional tracking, they have buttons and joysticks, but they're fairly limited in terms of the haptic feedback they can provide. If you think about when you're playing a game in VR, if you get hit, your controller might vibrate. If you touch a surface you're not supposed to touch, your controller might vibrate. If you get some kind of notification, your controller is going to vibrate. What if you could improve realism in virtual environments by conveying a more realistic sense of touch? Our Haptic Revolver device allows the user to feel not only touch contact against the fingertip, but also the motion of the finger sliding across various surfaces. You can also touch different objects in the scene and experience different textures and shapes of objects against your fingertip. Now we implement this using a wheel that moves up and down, and this allows us to provide touch contact against the fingertip. So we render virtual surfaces in the physical environment by having this wheel move up as you contact the virtual surface. We render motion and shear forces against the fingertip by spinning the wheel. So as you drag along a virtual environment or virtual surface, this wheel spins in the opposite direction to render that motion underneath the finger. By customizing these wheels, we can do some more interesting things. For example, we can put textures on the wheels directly, so you can touch an object and then touch a different object and feel a completely different texture. Finally, by 3D printing custom shapes directly onto these wheels, we can greatly extend the possibilities. So here we show how we can put different shapes directly underneath the fingertip. Researchers have explored some of these rich haptic sensations before. For example, there are robotic exoskeletons that provide force feedback against the fingertip. We've seen wearable devices that provide skin deformation on the fingertips. We also have robotic arms that are grounded that can provide force feedback against the hand and fingers, as well as provide haptic props against your hands just in time. There's another rich line of research around tactile arrays and shape displays that attempt to provide higher resolution haptic feedback. Now, if we take a step back, though, there's kind of this big gap between what's some of the awesome haptic stuff in the research community and what's possible on more mainstream devices. You can do a lot with a robotic arm, but it's not really feasible for that to be a consumer device in the near future. So I think part of the solution requires us to think about what's really possible on a controller form factor. VR controllers are great for input, as I mentioned before, but they're also easy to hold. You just put it on, you don't have to strap anything on, you pick it up and go. So our work falls into this category of holdable haptic devices, and it kind of explores what haptics are possible if we limit ourselves to this controller form factor. So our Haptic Revolver is a handheld device that's positionally tracked and renders 2 degrees of freedom underneath the fingertip. Again, this wheel moves up and down to contact the finger and then spins left and right to render shear forces underneath the fingertip. This is implemented in a controller form factor, so you just pick it up and go. Now, by combining these 2 degrees of freedom with the ability to customize these wheels, we can render many different haptic sensations without the need for extra devices in the environment. So we implement this device using 2 motors. Each one provides 1 degree of freedom. A servo motor located in the palm of the hand is responsible for moving the wheel assembly up and down to contact the fingertip. A DC motor located inside the wheel assembly is responsible for spinning the wheel and providing this kind of shear or motion underneath your fingertip. We use a high-resolution quadrature encoder in that DC motor in order to operate this motor in servo mode, so we can not only control the velocity of the wheel, but we can also control the position of the wheel and put different haptic elements precisely underneath your fingertip. Now, since we're spinning things underneath your finger, we really want your fingertip to stay in place. We don't want it moving left and right. So we have a groove on the top of the device. Your finger simply rests inside that groove, and it kind of keeps it fixed horizontally in place. Now, I mentioned earlier that these wheels are customizable. We actually had a lot of fun kind of exploring the design space of these wheels. Since they're easily interchangeable, you can either use a general purpose wheel for most of your experiences, or you can pop it off and pop on a new wheel that's custom designed for the VR environment that you're experiencing. So these wheels can contain, as I mentioned, different textures, or you can change the shape of the surface to provide simulate objects in the environment. Or you can put edges in the environment, so you can, if you want to touch a virtual button, you can move left and right and kind of explore the edges in the scene. Now, in order to make this work, we developed a Haptic Revolver rendering engine. It's responsible for analyzing the scene. It looks at what textures should be rendered on the fingertip and delivers the appropriate spot on the wheel directly underneath your fingertip just in time. One of the important parts of this rendering engine is actually examining the scene for boundaries. So it looks for when one material transitions to another, and it precisely positions those edges at the right spot. You can see an example here with two different surfaces. We have this blue surface that the user is dragging along, and this black surface that represents some object in the scene. Notice how we approach that black surface, the rendering engine positions those edges in exactly the right spot. Now, instead of going into all the little details about how we implemented this, I kind of want to talk about two main challenges that we faced. And one of them you might be asking yourself right now, you can explore a surface in 2 dimensions, but we only have 1 degree of freedom on this wheel. So we were really curious about techniques that we could use to approximate the sensation of sliding in a direction that we don't actually have a physical correspondence for. So there's a couple options we can do here. The first and simplest option is simply to use 1D motion. So when you move your hand right, the wheel moves left the same amount. And if you move vertically, the wheel doesn't spin at all. So that's what we call our 1D motion mode. We were curious whether we could simulate this in 2D as well. So in our 2D motion mode, we simply choose a direction to spin in, and so if you move your finger vertically, we spin the wheel horizontally. We kind of hypothesized that users might not be very sensitive to the direction of motion underneath their fingertip. So this is kind of velocity control mode. If you move with 1 meter per second to the right, the wheel moves with 1 meter per second to the left. And we wanted to compare that to a baseline condition, which we call shear mode. In this case, it's positionally controlled or angular controlled. So if you move your finger to the right with a certain speed, the wheel simply spins just a little bit to the left to provide a little skin deformation and tug on your fingertip. And we do this for the 1D mode and the 2D mode as well. So to understand how this works and how users perceive the haptic realism of these modes, we did a short user study where we had users trace 6 different paths. These consisted of vertical lines, horizontal lines, and then paths with various horizontal and vertical components in it. We did this for all 5 different wheel conditions. That's the 4 I mentioned, as well as an off condition where the wheel didn't spin at all. And after they traced these paths, we asked them how closely did the haptic rendering match your visual impression of the scene, and they rated that on a 1 to 5 scale. So you can see the paper for the full results, but on this graph here, you can see the vertical axis represents haptic realism, so higher is more realistic. On the horizontal axis, we have our different wheel modes. One thing I want to point out is that skin deformation alone here wasn't enough. So when we actually were moving the wheel underneath the finger, that provided a great deal more haptic realism to the users. We're also interested in looking at our 1D versus our 2D modes for the motion conditions. So what we found is that for many conditions there wasn't much difference, but in particular the vertical line condition. So if you're just taking your finger and moving it straight up, spinning the wheel in a horizontal direction, even though it's completely not the correct direction of motion, actually significantly improved the haptic realism. In other paths, such as paths with diagonal components, there wasn't really much difference between the 1D and 2D modes, and this kind of suggests that when you have some horizontal component of velocity, even though it's not exactly the right speed, that's sufficient to provide this level of haptic realism that we're looking for. Now I want to talk about a second challenge we faced, and this kind of arises when we start to think about more unique wheels. Maybe we put different textures on the wheels or various surfaces on the wheels. How do we actually, since the wheel geometry doesn't match one-to-one with the physical scene, how do we kind of do this alignment? One thing that we realized would be really useful is if we could kind of fudge the wheel speed a bit. So we introduce a gain term to our equation. So when we move 1 meter per second to the right, we move something proportional to 1 meter per second to the left. So we introduce the speed is proportional to the gain times our velocity. And so if our gain is 0, that means the wheel's not spinning at all. A gain of 1 is kind of a 1-to-1 mapping with the physical world. So a positive gain means that you're moving in the correct direction. A negative gain here, though, means we actually spin the wheel in the wrong direction. So we wanted to see how that would impact haptic realism, and it would allow us to put different features underneath the finger more efficiently. So we did a second user study where we invited users to swipe horizontally along a path under 17 different gain conditions, from negative 1.6 to positive 1.6, and this includes 0 for no spin, and then 1 for a 1-to-1 condition. And once again, we asked how closely did the haptic rendering match your visual impression of the scene. So you can see our results here. The first most obvious thing here is that this gain of 0 represents a very low realism score. So this suggests that spinning the wheel is better than no spinning at all, which is good because that's kind of the premise of our device. The other thing you might notice here is that this graph kind of appears to be a mirror image of itself. So when you spin the wheel in the reverse direction, users actually found that it didn't really impact the realism. Surprisingly, we didn't tell users what we were going to do, and only 1 out of our 12 users even noticed that we were spinning the wheel in the reverse direction at all. So this was a really cool result. The last thing I want to point out here is that once we get to about 0.6, it kind of tapers off. So that means that from 0.6 up to 1.6, what we studied, we can kind of fudge this wheel gain a little bit, and users don't notice too much. So this has a couple of implications for our rendering. Number one, we set our default gain at 0.6. This kind of makes our fixed wheel size and effectively scales it up a little bit. We also dynamically adjust our gain to put different features at the right spot. And finally, we introduce a new reversal technique to kind of mask features that we don't want the user to feel. So our default condition here is what we call the wheel dip condition. So let's say you're swiping along this blue surface again, and this black object is coming up. And maybe this is a rough texture that we don't want the user to feel. So our default condition, we simply dip the wheel down, spin a little faster, and once that black spot is on the other side of the finger, we bring it back up and the user continues swiping. We do this for small features. But because of the results of our user studies, we thought maybe it would be nice if we could just spin the wheel in the reverse direction. So in this new wheel reversal mode, when the black feature approaches your finger, we simply reverse the wheel direction and start spinning in the other direction. Now, putting this all together, we wanted to think about how we could take this and start to build interactive experiences around this. But we didn't want to just create a fixed experience with a fixed wheel. We wanted to allow users to customize the experience. So maybe a user 3D prints their own wheel at home or puts various textures on the wheel. So we have a very easily extensible wheel configuration file. So when you make a wheel, you just simply specify in this file which features are at which spot on the wheel. And our rendering engine is responsible for examining this file, examining the scene, and determining a mapping between objects in the scene and different textures in the file. Now I want to show 3 different demos that we made from this. This first one you may have seen at our demo reception on Monday night. This highlights some of the ability to do different textures and shape rendering on the fingertip. So here when the user touches a poker chip, they feel a hard plastic against their finger. When you touch the table surface, you feel this felt texture, and when you touch the card, you feel paper. And more importantly, you feel the boundary conditions between all of these. So if you touch the right edge of the card, you feel a paper felt boundary at exactly the right spot. In the second demo, we highlight how we can use shape rendering to make different virtual objects feel more realistic. So here the user's touching a virtual keyboard, but there are grooves in this wheel that kind of highlights the boundaries between different keys. So when you swipe your finger along the edge of this keyboard, it feels like you're swiping along the edge of a physical keyboard. And in this third demo, we wanted to look at different tools that users could use. So in this case, we have purely passive tactile cues on the wheel that provide some indication of a tool you're using. So when you push this can of spray paint, you feel a nub underneath your finger. And by sensing the force on the wheel, we activate the spray paint appropriately. So we invited 11 different users to try out this scene just to provide feedback, all 3 scenes. We performed a guided walkthrough followed by semi-structured interviews. And I want to share a few of the results. Encouragingly, users mentioned that this improved realism compared to a standard HTC Vive fiber tactile rendering technique. P10 said it actually felt like I was moving my finger along a table. But one interesting observation was that if we start to render these objects, we might run into a problem of an uncanny haptic uncanny valley. So P7 mentioned that it doesn't feel exactly like spray paint, but this is cool. I have a nice sense that I'm holding it. So by attempting to render the spray paint can at all, users started to pick up on small details that weren't quite right. It's also important to think about user preferences. We always go for realism in these kinds of things, but that may not be appropriate for all users. For example, P8 mentioned that it was hard to get used to it touching my finger. It felt more real, but that was a bad thing. If I had time, maybe I could have gotten used to that. In developing this project, it was a very iterative design process. We learned a lot on the way, and obviously there's a lot more we can do here. But for the sake of time, I just want to mention one interesting extension from this that we've started to think about. In all the demos I've showed, we've looked at purely passive wheels. We saw how passive tactile cues on the wheel can start to allow the user to feel tools. But what if we actually put active elements on the wheel? So here we show a wheel where we put input elements on the device. We have buttons, a little rocker switch, as well as a joystick for rotary controls. So in this case, the user is looking at a DJ mixer, and when the user touches a button on the mixer, they get that haptic sensation of the button, but they can also touch it and actually interact with the scene. And there's a lot more we can do with this, and we'd be excited to look for, to explore more of this kind of active design space. So I want to leave you with a few takeaways. Number one, haptic controllers offer an interesting space to explore haptics for virtual reality. Number two, the visual system is very dominant in a VR system. So this gives you a lot of flexibility to fudge some of the haptics and deliver features under the finger at exactly where you need them. Number three, users are fairly insensitive to the direction of motion underneath the fingertip. So this is an interesting takeaway for others working on haptic devices. And number four, using interchangeable haptic elements that allows you to customize the device, you can actually deliver the appropriate textures or shapes underneath the fingertip. You can allow more realism in VR. Thank you very much. I'm happy to take any questions.
Hey, how's it going? Darcy Philippon from Google. Question in regards to, so you mentioned realism, but how about like dexterity and accuracy? Did you find that this kind of haptic feedback helped people in VR be more accurate?
That's a great question, and it's one that we've been thinking a lot about. Particularly in the example I showed with the text entry study, it'd be very interesting to see if rendering these edges will allow you to be more accurate. That's something we thought a lot about, but something we haven't quite gotten to in this study.
Got it. Thank you so much.
Thank you.
Hello, this is Taejun Kim from KAIST. I think the grabbing situation is limiting the usage of finger as a single finger usage. So I want to ask, do you have any plan to extend it to the multi-finger usage scenario?
I'm sorry, did you say the grabbing?
Yeah, like the grabbing, the form factor makes it only using the one finger, right?
Yes.
So
yeah.
I'm curious about that. You have any further plan to extend it to use, it can be used in multi-finger?
Yeah, that's an interesting question. I think for haptics in VR, you don't necessarily need this on every finger. And it's important to think about what features you need for each finger. We chose the index finger for this device because that's an obvious one that users will interact with. Most users will choose to push a button with their index finger, for example. I wouldn't suggest making this device where you try to do it on all 5 fingers, although that would be really cool. I think one thing that would be an interesting extension of this is to think about gripping devices. So if you we're looking at mostly surface interactions, but you can also grab different things in the scene. And there's an interesting talk coming up right after this, actually, that looks at grabbing devices. So I think it would be a very interesting conversation to think about how we could combine techniques from this work as well as this next work to think about grabbing as well as simulating things on one finger.
Okay, thank you.
Hi, Sean Fulmer, Stanford University. Great talk, really exciting work. I was wondering if you could talk a little bit more about when you were talking about potential solutions to running out of the workspace, and you mentioned this idea of changing the direction of the wheel. And I'm wondering if you tried that out. It seems like, basically we would be more easily perceive these changes to direction and also maybe changes to acceleration than being able to tell which direction it's in. So
That's
I'm
exactly
wondering
right.
what would that experience be like, and if you've tried it?
That's exactly right. And as I mentioned, we do have these 2 different techniques because as the wheel reversal, you don't necessarily notice the direction in which you're going, but you're right, you do notice the change in direction. And we have a couple ideas for how to make this less noticeable, although we're never going to be able to fully eliminate it completely. One thing we observed is that if the user is pressing down harder, so if there's more contact there, there's less, well, one thing that you would observe is if you're touching loosely, when the wheel moves in the opposite direction, your finger jerks a little bit in the other direction. That's what makes it very noticeable. So if the user is making firmer contact with the wheel, this becomes something less noticeable. So we've thought about different techniques to maybe put a little strap or a little rubber thing in there so that the user's finger is pressed down a little bit more. One thing you could do is also raise the wheel a little bit higher. But really, the goal here would be to minimize this kind of back and forth motion.
Nice, thanks.
Thank you. All right, thanks everyone.
Okay, thank you.